Alright, to start with today, I want to kind of rehash what we did yesterday with momentum and impulse and the relationship between the two. So the first thing that we did yesterday was we talked about momentum. Now, we gave the symbol of momentum, or we gave momentum the symbol P, and the momentum was equal to the mass of the object times the velocity, where P equals mv. Now you should know that mass is measured in kilograms, velocity is measured in meters per second. So when you multiply the two, you'll get a unit of kilogram meters per second. And we discussed momentum as being kind of the oomph of an object, or a property of the object that is very much related to the inertia of the object, which says that if it's moving, it really wants to keep moving, and that the momentum of the object is really what makes the object hard to stop. Now, if you look at your worksheet here, there are a couple questions that deal with just what is the momentum of the object, and these are fairly easy to do. I'll do the first couple of them with you. So the first one, it says, what's the momentum of a 3 kilogram object that's moving at 5 meters per second? This is as simple as taking your formula, that P equals mv, and plugging in your values. So your mass is given to be 3 kilograms here, your velocity is given to be 5 meters per second. 3 times 5 is going to be 15 kilogram meters per second. And that's all there is to that problem. The next one, number 2, is a little bit more difficult, but not really. Again, you start with your formula that P equals mv, and that your mass here is now 9 kilograms, and your velocity is negative 1.5 meters per second. Now, I should remember that if you have a negative sign on the velocity, that just means that it's going in some direction other than positive. So if we say that positive is to the right here, then this velocity here is going to be going to the left, just against the positive. So here you multiply 9 times negative 1.5, and you get a momentum that is going to be negative 13.5 kilogram meters per second. And again, this negative sign here says that this momentum is just, again, traveling in the direction that is against our positive direction that we assigned over here. So those are pretty basic. Now, after we did momentum, we decided to go on to impulse. Now, we said the impulse was just basically a change in momentum. And since momentum is based upon the mass of an object times the velocity of the object, if we have a change in momentum, then we're also going to have a change in velocity. Now, a change in velocity is what you know as acceleration. And we really talked about acceleration when we did Newton's second law, which says that F equals ma. So, if we have a change in momentum, that means we have to have a change in velocity, and a change in velocity is basically the same thing as a change in acceleration, and to cause a change in acceleration, we need a force. Now, for the amount of time that the force acts, that will cause a greater acceleration, which will cause a greater change in velocity, which is a greater change in momentum. So impulse can also be defined as the force of an object, or force that acts on the object, multiplied by the time that the object acts. So we have impulse being force times time, or it being a change in momentum, which gave us two formulas for impulse. First thing we know, or that I told you yesterday, was that impulse was given the symbol J. I know it makes perfect sense, not really, but J is what the symbol is, so learn it. And we have two formulas. J equals delta P, where delta again is change, so that's going to be the final momentum minus the initial momentum, or the change in momentum, which can also be written as mass times your final velocity squared. This is our final momentum here, minus the mass times the initial velocity, or our initial momentum there. And if you want to take it one step further, for objects that, or for single objects where the mass doesn't change, you could use your algebra to say this right here is going to be the mass times the final minus the initial velocity. But if you don't want to do this step right here, you don't have to. I'm perfectly fine with you sticking with this value right there. So the other thing that we know impulse was equal to was force times time. And both these formulas are very valuable. Now, going back to our algebra formula, that if we know that A equals X and that B equals X, then I can say that A equals B. It's just simple algebra. I can say that if J equals force times time, and that if J equals delta P, that force times time equals delta P. And this right here is very useful when we talk about a force that causes a change in momentum, or how long a force needs to act on an object to cause a change in momentum. So, back to our worksheet. So from 6 to 25, all of these right here are asking for a change in momentum, or an impulse, or a force, or a time, which are always going to be talking about some of these variables right there. So, let's look at number 6 to begin with. Just do a couple with you. It asks for what is the change in momentum. Anytime you hear change in momentum, that is just a long way of saying impulse. So, what is the change in momentum or the impulse of a 3 kilogram object accelerating from rest to 12 meters per second? Now, you know the impulse is equal to delta P, which is the same thing as saying mvf minus mvi. So in this case, we know our mass of the object is going to be 3 kilograms, and our final velocity is going to be 12 meters per second. Now our initial mass is still going to be 3 kilograms, didn't change, but our initial velocity is rest, which means that's 0 meters per second. Now, if you have 3 times 0, that cancels out because this whole thing right here becomes 0, and I have that my impulse or my change in momentum will just be this 3 times 12, which is equal to 36 kilogram meters per second. And that's all there is to do on that one. Now, if we look to number 7, 7 says you have a 4 kilogram object accelerating from 10 meters per second to 12 meters per second. So again, we're asked for change of momentum or impulse. So J equals delta P, which is mvf minus mvi. Pardon my handwriting here. So we actually have 2 different velocities times, so we have to use both sides of the equation. So our mass of the object is going to be 4 kilograms, so that will be where your m value is. And your initial velocity is going to be, your final velocity, because we want to do final first, is going to be 12 meters per second. And then you will subtract the initial, which is again, the mass is 4 kilograms, and your initial velocity is 10 meters per second. So 4 times 12 is going to be equal to 48 kilogram meters per second, minus 4 times 10, which is 40 kilogram meters per second. 48 minus 40 is equal to 8 kilogram meters per second. Now, that was the long way of doing this, where we use the formula mvf minus mvi. Now, if you want to use a shortened formula for it, the one we talked about here, it does make it a little bit easier to do with the calculator. So, doing the same problem again, we're still doing number 7, but this time we're going to say that J is going to be delta P, which is equal to your mass times your final minus initial velocity, because this right here could be distributed to create the formula we did last time. Same problem, just another way to do it. So you're given again that mass is 4 kilograms. 4 kilograms, and then we're going to use this little change in velocity formula here. So we're told that our final velocity is 12 meters per second, and that our initial velocity is going to be 10 meters per second. Now 10 minus 12 is 2, so 4 kilograms times 2 meters per second is going to be 8 kilograms meters per second, because 4 times 2 is 8. So, simple enough. Now, on the sheet, they make a very specified effort to tell you that change in momentum is the same thing as impulse. So, if you really look close at it, 6 through 9, or 6 through 10, excuse me, this is actually the same thing as 6 through 15. But if you want to rework them, hey, it's good practice. Now, let's look at number 16 next, because it asks for how much force is being created or exerted on a 3 kilogram object accelerating from rest to 12 meters per second in 1.5 seconds. So, since we're looking for a force here and we're given a time, we know that we have to use our second impulse formula, which says the impulse is equal to force times time. Now, we're not given the impulse, but we're told that we have a 3 kilogram object which is accelerating from rest to 12 meters per second. So we also have to use our delta P one. Now, remember the last kind of formula I told you when we did our little algebra thing where you said that A equals X and B equals X, so A equals B? We can say that if J equals Ft and J equals delta P, that Ft equals delta P. Now, one thing that makes this right here a little bit easier for you is that you should notice that this delta P right here is going to be of a 3 kilogram object that's accelerating from rest to 12 meters per second, which is the exact same thing as number 6 and number 11. Now, if you go back and look at number 6, you should find that this delta P is going to be 36 kilogram meters per second, because we said 3 times 12 is 36, and since we don't have an initial velocity, then there's no initial momentum, so that's going to be your impulse. So, our force times time here will equal 36 kilogram meters per second. So I'm looking for my force, and I'm told that my time is 1.5 seconds. Now this will equal 36 kilogram meters per second. And if I divide seconds by kilometers per second, that gives me kilogram meters per second squared, which is force. So, to solve for F, all I do is I simply divide each side by 1.5 seconds. My handwriting here is atrocious. I apologize for that. And I get that 36 divided by 1.5 is a force of 24. And since we're talking about force here, that unit will be newtons. And that's all you have to do on that one. Try one more. Number 17. It says how much force is exerted on a 4 kilogram object accelerating from 10 meters per second to 12 meters per second in 2.5 seconds. So again, we start with the exact same way we did the last one. We know that impulse is equal to force times time, and we know that impulse is equal to our change in momentum, delta P, which is basically mvf minus mvi. Now, again, we're going to make our substitution that says that our force times our time is equal to delta P. And if you look at number 11, this delta P right here is the exact same thing you had to solve in number 7. So back to look at number 7, where you said that 4 times 12 is 48, and 4 times 10 is 40, and that the final momentum minus the initial momentum, or that 48 kilograms per second minus the 40 kilograms per second, gave you a change in momentum of 8 kilogram meters per second. And that's just the same thing we found for number 7. So if we look at our force times time, we're asked for the force, so if we're looking for F, we're told that the time here is going to be 2.5 seconds will equal 8 kilogram meters per second. And again, if we're solving for our F value there, then all we want to do really is, let me erase that part. All we need to do is divide each side by 2.5. Make sure those cancel out. 8 divided by 2.5 is going to be equal to 3.2 newtons, and that is our force. And that's all you have to do on that one. Now, a couple more. Let's just go on to number 21. And number 21, you're asked to find time. So this is very similar to the last one. Again, we're starting with J equals Ft, where impulse is force times time, and that the impulse is going to be delta P, and we're going to combine them together to say this force times time is equal to our change in momentum. Now, if you look at number 21, you again see that you're talking about a 3 kilogram object going from rest at 12 meters per second. That means this delta P right here is going to be the same thing as number 6, number 11, and number 16. They all use the same change in momentum, which, if you look at number 6, is going to be 36 kilogram meters per second. Now, we know that our force times time will equal to 36 kilogram meters per second, but last time you wanted to know the force, this time you want to know the time, and we're given a force. Let me find our eraser. So your force was told to be 2.5 newtons. So 2.5 newtons times your time equals 36, so we want to divide each side by 2.5 newtons. Those cancel out. 36 divided by 2.5 will equal a time of 14.4 seconds. If I did my calculations right. Yep, 14.4 seconds. Which says that if 2.5 newtons acts for 4.4 seconds on a 3 kilogram box, it'll make it move at a final velocity of 12 meters per second. Alright, one more. And I'm setting y'all free to do the rest of these on your own. So, again, for number 22, you're told that how much time is needed to accelerate a 4 kilogram object from 10 meters per second to 12 meters per second if a force of 2.5 newtons is applied. So again, this is just like number 7, 12, and 17. Again, start the exact same way we've done the past few of them. J equals Ft, J equals delta P, that's supposed to be a J there. And I can combine these to say that force times time equals delta P. And then this delta P right here is the same thing as number 7, which is 8 kilogram meters per second. Basically, 4 times 12, which is 48, minus 4 times 10, which is 40. Our final momentum minus our initial momentum, so what we're talking about there, 48 minus 40, is 8 kilogram meters per second. And that equals our impulse, which is the same thing as force times time. Now this time we're told that a 2.5 newton again causes this change in momentum. So our force is going to be 2.5 newtons. And we're looking for our time. And this right here will equal our impulse. So, again, to solve for time, we divide each side by that force. And 8 divided by 2.5 is going to be 3.2 seconds. Notice right here is the same magnitude as number 17 because, again, using the value of 2.5. 17 uses 2.5 seconds, and 22 uses 2.5 newtons. But since this multiplied together is going to give you the same values, the units change. And y'all should be able to do the rest of these by yourself. So good luck.